Good evening, all. Welcome to this week 5 webinar series on quantum algorithms using Qniverse. Last week, Mr. Harishankar demonstrated or introduced last week, Mr. Harishankar introduced the Deutsch-Dosa algorithm, which demonstrates the quantum speedup. To recall, what does Deutsch-Dosa algorithm do? Given a function, we can query the function whether it is a balanced or a constant in one quantum query when compared to multiple classic. So the DJ algorithm showcases how quantum parallelism and interference can solve specific problems exponentially faster than classical algorithms. So moving on to this week's session, before we get into the session, a few announcements. Recently, we released Quantum Vibes Q2 edition of 2025. It is available in quantum.net website. You can all have a look at it. This week's edition, we have interviews from leading researchers and industry experts from India and abroad. Then we have research articles from various researchers, then quantum currents and the job opportunities around quantum technologies, the publications and the quantum events. And if I recall correctly, in our inaugural Quantum Vibes edition, we had Professor Amlan's article on breaking the limits, exploring the possible capabilities of quantum computing, the capabilities and opportunities, way back in March 2023. Okay. So moving on, we have a WhatsApp public channel called Qniverse. It has been published in our qniverse.in website. So please do join whoever have not joined for getting the latest updates on the platform, the Qniverse platform, or the webinar related information. And regarding the presentation materials of this webinar series, we will be posting it through our various communication channels like GitHub or WhatsApp public channel or Zulip platform. And post session, we will have a short quiz wherein you can recall your learnings and recall your learnings of the session. And please keep the chat clean. Don't post unnecessary chats. Request you to put ask your questions to the speaker. And you can share your experience video testimonials and get rewarded. You can record 1 minute video on your genuine experience of the Qniverse platform. So what does it and share us with us through qniverse@cdac.in email ID. So with this, what you will get a chance to visit our photonics lab here at CDAC Bangalore, and you can have a first-hand experience on how a quantum computing through photonics is being explored. And also you will get 100 points, the credits on Qniverse platform. Moving on to today's session, we have with us Professor Amlan Chakrabarti, who will be sharing his insightful experience in QFT and QPE. He is a distinguished academic researcher with expertise in quantum computing, artificial intelligence, and cybersecurity. He currently serves as the director and professor at A.K. Choudhury School of Information Technology, University of Calcutta. He earned his PhD from Indian Statistical Institute and University of Calcutta with a specialization in architectural synthesis of quantum computers. With over 2 decades of experience in teaching and research, he has supervised more than 20 PhD research scholars and 4 postdoctoral researchers. He holds 6 patents and a copyright for 3D reconstruction and slicing of MR images of the brain. He has authored numerous research publications and books and has led several national and international R&D projects funded by prestigious agencies, including MIT, DRDO, and DST. He is widely recognized for his academic leadership and efforts in promoting quantum technology, education, and innovation in India. We have a long-standing collaboration with Professor Amlan from CDAC as well. Uh, with this, I welcome you, sir, for this webinar series of week 5. And thanks for graciously accepting our invitation to deliver a lecture in this session. Over to you, sir, now.
Yeah, thank you, Santosh, and thanks to SIDAC Bengaluru, for inviting me, and obviously that means my journey of quantum computing is now touching 20 years, and obviously that means I am very much uh, well connected with what SIDAC is doing, right? And it's really good to work with SIDAC in the domain of quantum computing, because they have a beautiful team, they have good infrastructure, they have knowledge, so it's lovely to work with all of you. So today's discussion, or what I will deliver, is a very interesting topic of quantum algorithm, because when we say that why we should go to quantum computing, the principal thought process is that, can we show quantum advantage? And what I will discuss today, basically the quantum Fourier transform, and one of its application of quantum phase estimation. That will really show you that what we can do with the real data, right? And how we can leverage quantum computing in real data processing, because when we say Fourier transform, it is related with so many applications in computing, communication, right, and so on. What I will also try to give you a brief overview of what is Qniverse. This is a very good platform which is being developed by the scientists and engineers in CDAC, and we are also working with Qniverse platform. My students are now getting involved to work with the platform, and I am also exploring the platform. A lot of things will be coming up, I think, in a sequence of Qniverse platform, and I hope that in this particular talk you will also get into that how we can use the functional models of Qniverse on the topics what I discussed today. So let me start my presentation. This is a 1 hour, right? Our lecture, right? So let me start my sharing the screen. Okay, right. So can you see my my presentation?
Yes, sir.
Okay, so good. So it's very titled. It's a very fundamental presentation, but which discusses 2 key concepts. Of quantum computing, and we will see that how the problems which are super polynomial or exponential in the classical domain, can be reduced to logarithmic order, right, in the quantum domain, by leveraging quantum advantage. So I will first start with quantum Fourier transform. And as we know that the Fourier transform has a discrete domain equivalent called DFT, and the equivalent in the quantum domain, is basically called the quantum Fourier transform. Right? And this quantum Fourier transform is basically how to use the qubit states to represent your sample sequence, right? And how to do the Fourier transform more as a concurrent operations, okay, compared to the sequential operation what we do in the in the case of classical sequence, classical or a discrete Fourier transform of a sequence, right? And this is primarily due to the utilization of the quantum state representation of your sequence, and actually that is doing over a over a over a superposition of basis states, and that helps us to actually do the transform on all the samples of the sequence at one shot, right? And leverage the stuff. Okay, so so this is just to before we go to the quantum Fourier transform. Okay, I just tell you about the discrete Fourier transform. Okay, which is basically we have a sequence which is identified. Let me use a laser pointer. Okay, yeah. So, yeah. Okay, screen bar. Okay. So this is my sequence, right? Which is a sequence having capital N samples. Okay, right, and we index them to x0 to x capital N minus 1. And what we try to do, we will generate the equal number of Fourier coefficients in the DFT domain. But how we do that? We do that with a series summation and with an and with exponential term, okay, which is actually goes by k small n by capital N. What is k? K is the particular sequence of the Fourier coefficient. So capital Xk is the kth defines or states the kth coefficient of the capital X series, which are the capital X series is the frequency component or the elements of your Fourier, that is, or the Fourier coefficients, okay, of the terms in your Fourier series, okay, right? And so each of these kth index of your Fourier sample is defined by this operation, where small n is the index of the temporal domain sequence. Temporal domain sequence, and capital N is the length of this sequence. Okay, so these are the things what I said, right? And so this operation is being done for each of the capital Xk. Okay, so if you try to look into that, how many operations I need to do, right? You can easily find out that this particular operation, okay, which is a sort of a product operation, okay, needs to be done for all the for each element. I do obviously the n this product operation, which is of the order of n, right? And this I do for n elements. So it is ideally n square, capital N square operations. What we need to do to find the Fourier frequency components of a time domain sequence. Okay, right? This is an inverse transform. You do an and so so the basic mathematical trick is that here we find the power as minus, and here we find the power as plus. Okay, right? And this xn is again, and here we take xk as the input, and we generate small xn as the output. So this is again, we come back to the time domain sequence, right? And can generate the sequence. This is called the inverse Fourier transform, or on a discrete domain is called IDFT. Discrete domain because I'm working with a sequence, discrete sequence. Okay, right? And this can be this particular and transform. What we do actually, if we look into here, there are two vectors. Okay, one vector is a capital X vector, and another vector is a small x vector. And now if we try to do a vector representation, then actually what we do, this is the transform matrix. Okay, so this matrix D, okay, multiplied on X will generate capital X. Okay, right? And that is you see that this is basically for the capital X0. Okay, this coefficient, these terms are for capital X0, this term is for capital X1, and this term is for capital Xn, right? Okay, right, and that's why, and that's why you will see there are, in this particular transform matrix, there are capital N rows and capital N columns, okay, because each of these are basically for capital Xk. So, so if I write the transform is actually, if I try to the vector notation, let me just use a pen. So if I just use a pen, okay. So in the notation, it is capital X is equal to d of small x, okay, right? And that's the d multiplied by small x, and that's the way you define it as a n cross n matrix, which is basically n square operations, okay? And every nth entry is basically this particular term, which is e to the power minus 2 pi k small n by capital N, and this is basically for the discrete Fourier transform or forward discrete Fourier transform, okay? Okay, right, and so this is notation what I already showed you, okay? Capital X equals to d dot small x, right? And this is the smallest vector, which is a time domain sequence, and this is the capital X vector, which is the frequency, domain coefficients, okay, right? And we generate it. Okay, now let us see. Now let us after this understanding that what we need to do in a discrete Fourier transform, right? Can we take it into quantum domain, and we try to find that how we leverage this, leverage the quantum state space, okay, or the superposition state space, okay, of the quantum system, okay, to gain certain advantage, okay. So what we look here is that, hey, first of all, we have to encode the sample sequence on the qubit state space, right? And there are several techniques out there, okay? There are several techniques out there. So, but what we need to do, we need to generate AX of this particular, we have to generate, let me again come back to this point. We have to generate this AX, okay, for the X. So AX is the amplitude of the state X. Okay, right? And what are these state X? These state X are corresponding to the sequence. And how many qubits I will require, right? Okay, I don't think I can get a question answered here in the session, but in the class, if some of my students have joined here, they know that I always interact and try to get the answer from my students. Okay, so if we look here itself is an advantage. Why? Because if you have a sequence of capital N length, okay, in quantum, you can represent that sequence by log of capital N qubits, because log of capital N qubits will generate capital N basis states in a complete superposition. So if your sequence length is capital N, of your time domain sequence length is capital N, you use log of capital N, okay, log base 2 of capital N number of qubits, and generate it in the superposition, right? And this amplitudes will be responding to each of the indexes of the values what we have in each of the indexes of your sequence. So if we have a sequence of 16, right? If you have a sequence of 16, right? Okay, so you take 4 qubits, generate all possible states, which are 0, 0, 0 to 1, 1, 1, 1, right? And so so which was, here see the value of x0, sample of the small x sequence will be now taken as the amplitude x. and then the x1 will be the amplitude A1. Okay, like that, right? You go with A15, okay, the amplitude of basically x15. Okay, the small x15. So, okay, so I don't know whether, okay, if I try to again go by the pointer, I don't know that how many of you got it from my description. Let's go a little mathematical. So it means that, okay, so it means suppose I have a sequence. Okay, suppose I have a sequence. Okay, let's work with the smaller sequence for the time. Okay, so let us have a sequence of 1, 5, 7, 8. Okay, these are four. Okay, these are four four samples, and this is my small x. Okay, this is my small x. Okay. This is x0, this is x1, this is x2, and this is x3. Okay, now to represent these four, I require 2 qubits because 2 qubits can generate states 0, 0, okay, 0, 1, 1, 0, and 1, 1. Okay. Now the thing is that this 0 index is mapped with 0, 0 state. This one is next 0, 1, 2 with 1, 0, and 3 with 1, 1. Now the answer is how we push 1, 5, 7, 8 to these amplitudes. Okay, the only thing what we have to do here, that the amplitude square should be 1, and that's what's the qubit state encoding. So you cannot just put here, okay, I cannot tell 1 is the amplitude of 0, 0 state, 5 is the amplitude of 0, 1 state, 7 is the amplitude of 1, 0 state, and 8 is the amplitude of 1, 1 state, because that then I will be not doing justice to the inherent concept of superposition. So what I need to do, I need to normalize them. So normalize will be root over of each of them normalized with 1 square plus 5 square plus 7 square plus 8 square. So the amplitude of this, okay, this of 0, 0 will be 1 divided by this, right? This if I tell as p. Okay, so the amplitude ax of the 0, 0 state will be 1 by p. Amplitude of 0, 1 will be 5 by p. Amplitude of 1, 0 will be 7 by p. Amplitude of 1, 1 will be 8 by p. Okay, and this is the way how you first encode it, right? And once you understand this, I think everything is very easy to you. Okay, so this is the first step. This is the first step. How we generate the superposition. I've just defined the superposition in terms of small n equals to 2 here. Just understand, I've given a very toy example. Small n equals the same equation, small n equals to 2. For this example use case, 4 samples in a sequence will work out. But now you can just expand it to 16 samples, 32 sample sequence, 64 sample sequence, and you see how less effort you require in terms of resources represent that sequence. Okay, I will a little bit rub this because this becomes a little bit clumsy now. Okay, let me see if I can use this eraser. Yeah, so let me rub this out to make this a little bit better. Okay, I come back to this to my discussion. So once I did this, then my job is pretty easy, right? Then my job is just to generate the xk's now. I have encoded the small x. Now I have to generate capital X. So to generate capital X, what I do, I actually do this operation, and this is the QFT operation. So you need to generate an U operation. So now if this is your psi, QFT on psi is an operation which is an U operation, which is a combined sort of quantum operation on this quantum state psi, which will generate a state of this. Okay, and now what is this? This state is again a superposition on K, right? And what was K? K was basically the K was basically the the sequence of your Fourier coefficients. Okay, so this operation which you have to define with some quantum circuit on your state psi will generate a particular state, quantum state like this. Okay, and this operation will be done pretty easily because why? Because it will generate all the k, all the coefficients for all the k simultaneously, because now k's are also in superposition. You don't have to generate x0 first, x1 then, x2 then, and xn. You don't have to do and your capital N computation for each of them, and there are n such computations you have to do, which is n square in the case of classical in the discrete Fourier transform in the classical domain. Here you have to only do this computation over the superposition states, and it will generate all the k states in superposition, all the Fourier coefficients in superposition with a normalization factor. We see the amplitudes will be normalized here, and you can always get the normalization factor because all these terms are known to you. Small n is known to you, right? You can get back. Okay. So now this operator is the QFT operator, and your quantum circuit design means that, hey, can we design that means a unitary operation which can do this on the position state. So it is the operation is from a to the power x to this particular operation. That means x. That means from superposition of from the on ax, and we apply e to the power 2 pi ax to the power n. Can we actually do a quantum operation which will generate the superposition amplitudes instead of ax, but a term associated with ax like this? Right? And it's very clear that this is a sort of a phase operation, right? And we know that there are controlled phase operations which can do this operation. Okay. These are the mathematical functions which are associated in the quantum domain, or unitary transformations which we need to construct in the quantum domain, which can generate this particular term, okay, from X, right? And if you look into this form, right, we will try to make it a little bit what I can say, it's a little bit a sort of generic representation. Okay, so generic representation, if you try to go back to your a fundamental DFT, right, we can represent this matrix, the transformation matrix D, in this form, right? And this transformation matrix in D, we will represent this e to the power 2 pi I k n as a sort of omega, right? And that we will try to do. Okay, and that I will try to do. Okay, so what we need to do, we need to actually develop this for an n qubit system where capital N is equal, log of capital N is equal to small n, or capital N equals to 2 to the power small n. Okay, so can we do this by a quantum circuit of size polynomial in the number of qubits? Okay, and that's the way. So what we try to do, we try to actually, this will be your transformation matrix. Okay, because in the case of if you want to make a unitary synthesis of this particular matrix in terms of unitary operations, okay, that is the way we can construct the circuit of the quantum Fourier transform. Okay, right. What are these terms? If we just go back to DFT, I will just mention this. So if you see, these are the terms. Okay, so what is W? If you try to mention here W, so these are all ones, because Okay, okay. So if you look into this particular matrix, so you see that e to the power minus 2 pi I, okay, and then the capital N divided by capital N and the small k, this together actually defines your W, right? Then you have W1 N, which means that this is small n is 1, right? This way it goes on. So you can just observe this W, you can go back to that particular values, what is the omega, yeah, that means you can still small w, okay? So the small w values, what are those small w values? It is basically e to the power 2 pi I k is the small w, okay? And then it comes small n by capital N, and this small n is basically is defined by this index, the super okay, the superscript part, okay, and subscript part is your capital N, okay. So this is the way you can actually, and the dimension of this depends on the number of sequences of the samples. So the thing is that you have to construct this matrix in terms of the fundamental quantum operations, and then you are done with QFT, okay, often sequence capital N, okay, right? And this is the circuit operation by which you can actually achieve this, okay. These are control rotations, and you have to justify that why these control rotations can generate those type of terms on this thing, okay. So the first you see what happens is the superposition. So you actually superpose all your qubits, okay, right? And you superpose this in a sort of a sequence, so that, okay, so that you can actually construct the control qubits at first on the entire superposition of x1, and then the control of x2 on the entire superposition of x2, and this way it works out, right? As we know, the Hadamard gates does a superposition, and then there is a swap operation, because actually there is a there is a change. Actually, if you see this, okay, this one will be most probably the capital Xk, and this one with the most probably the capital X0. Okay, that means X, sorry, capital, yeah, this one capital, if you the one too small n, you can tell capital X1, right? And this one will be capital Xn, or capital Xk, sorry, capital Xk, and this one will be capital X1. So to make it in the same order, both the input small x sequence and the output capital X sequence, you require a swap gate, okay, to do that, okay? So this is the way it does, and you see that what are these control rotation gates? These control rotation gates are basically e to the power I to e to the power 2 I to the power k, and this is the way how you parameterize the RK gates, okay? So this k is similar to this 2. So when you write R2, this means it is 2 to the power 2. When we write R3, it means 2 to the power 3. When we write Rn, it's 2 to the power n, right? And if you go back, you will see that this exact transform implements okay, this entire transform implements this particular operation what we try to work out as an QFT okay, QFT quantum block, okay. And this QFT quantum block can be exactly synthesized, okay, by a sequence, by an iterative sequence which is like this, okay. And I said that swap gate is just to bring the order of the input sequence and the order of the output sequence in the same manner, okay. So this is the detailed things. I don't know how much time I have, so you can just try to see that. That means what is the QFT on a single state, right? And then you can work on the superposition state. So this is a QFT 4, okay, which means that you are actually doing for n equals to 4, okay, where actually you are multiplying this term a particular state, okay, right? And this way you can actually go like this, okay. That means you can actually see that what has been done there in the circuit, right, and what we do in this. So So this would have been a particular transform for n sequence of four, right? And this we try to see how it works out. Okay, and that's the way we try to explain that why that circuit Hadamard transform and the control operation transform together can actually generate this QFT function in the quantum state. Because you have to do that because in your primitive or actual quantum operations, you don't have anything apart from a single qubit, which is Hadamard, but we generate the superposition, and a two qubit control operation, which is a control phase operation in this particular case. Okay, right? And slowly, if you go through this example worked out, you will see slowly how this exponential term or the W term, what I have defined in the matrix form, gets built up. Okay, this is for a two state, okay, two qubits, right? And you can just expand this for n qubit, and you can find what is done. Okay, so if you look into this particular term, you see that for this particular term, already this term is basically for x2, and this term is basically for x1. Okay, so that's why we need to do a swap. Okay, and that's why you see. So this is basically for the way we do. Okay, and so now I will just come back to a typical classical example and try to make you understand that how we do it in reality. Okay, the first example I will tell, that says I have the classical sequence of 1000, which means that this is a sample sequence. So as this is a sequence having four states, so you require two qubits. Okay, so you require two qubits to encode. Okay, so what I encode this in this form, right? And this encoding is perfect because you know that in this case, that means all other states having zero amplitude and only the 0 state is there. Okay, so ultimately the x is only 0 0. You know, this particular very typical easy choice of my example. Okay, right? And then we do the QFT. Now if we do the QFT of the state, this particular state, right, will this particular QFT of 0 0, which is basically applying this function. Okay, capital N is 4, small n is capital 2. Okay, so with that, right, and k is also 4. Okay, with that, if you try to work it out, you will find that this will come up. This will come up as a sort of a sequence what you have to do. Okay, yeah. So you can see that this is the QFT output, right? And so what happens is that all the, in a case of 0 0 0 0, you have the DFT sequence which are all are present in this DFTX, which means that that means it is a perfectly superposed in the case of a DFT. Okay, now there are some other examples where X is not so trivial. Okay, then this is the way how we encode X, because why? Because this one is 0 0 and this one is 1 0, so you can encode this X in this form, and you can again apply the QFT. Okay, QFT on the state 0 and QFT on the state 2. So these are the ways you will get the values of QFT of 0 and QFT of 2, right? And then you can just actually couple those, sum those, right, and get the QFT of the sample sequence X. Okay, these are the ways you can just do by hand or do by very simple operation. There are some more examples where you're a little bit complicated, where you have the little bit larger sequence, you have to normalize them, right? And during normalizations, you have to find what are the amplitudes you generate. Okay, right? And so it will be, as I showed you, generically you have to do the normalization of all the amplitude, square them and sum them. That will come to the denominator. right? And this part will come to the numerator. So whatever the actual samples will come in the numerator values, and the denominator will be the normalized the sum of the square roots, squares and the square root. And this is the way you generate the sequence, and then you can again do the same transform, and you can get back what are the QFT values. Okay. Okay. So here I stop a bit, right, and I just come back that. Let me. Okay. Here I stop a bit and come back here to all of you. Okay. So sorry to all of you, and try to tell that. Okay. Okay, and try to tell me that. Okay, try to. Yeah, that I can. Yeah, try to get back to you on the sense that can I simulate this in Qniverse? Okay, there are a lot of ways of simulating this in Qniverse. Okay, and what I will do here. Let me see where I have the Qniverse stuff. Okay. Let me see if I can connect to the Qniverse stuff. Sorry. So let me go to the
Sir, it is QNIVERSE, sir.
QIUV, yeah.
QU is not there.
Qniverse, right?
NI, just NI.
Yeah, Qniverse. Oh,
Yes.
that's NI. Okay, sorry. So I think it is what? Let me see. Okay, yeah. So this is okay. So this is the Qniverse platform. Okay, that means I hope that all of you can visualize this, right?
Yes, sir.
Is it?
You may
Okay.
continue.
So yeah. So now what I show here is that these are the gate libraries, right? What you can have, right? All the single qubit and all the single qubit gates of various forms, and these are the 2-qubit gates. Okay, and this is a general unitary matrix, unitary gate. Also, you can implement. Okay, right? And there are okay functions which are directly there. Okay, due to that means you can always. Okay, suppose I just want to. Okay, I want to construct something on this Q0. Okay, right. Okay, right. And if you try to set this Q0 right, you can actually. Okay, this is the general form of any qubit we know, right? The general form of any qubit is a psi alpha 0 plus beta 1. Okay, alpha mod alpha square is the probability of getting measured as 0, and mod beta square is the probability of getting measured as 1, right? And it's called a mod because alpha and beta are generally the complex amplitudes. Okay, that's why we have alpha has two portions. One is the real and one is the one is the imaginary part. Okay, so just to make the things a generic alpha beta, this is a very good setup. Okay, if I want to tell that alpha will be 0, that means your first Q0 will be 0. Okay, then it is the alpha will be 1. The amplitude of 0 should be 1, and the amplitude of beta should be 0. If I want to set Q0 as 1, then the amplitude of alpha should be the alpha value should be 0, beta value should be 1. So this is the way how you can save it. Okay, how you can save, right? And if you just apply one Hadamard on a get set which is 1, right? You can run that. And there are options, right? There is this is working on the server of SIDAC. Okay. Now there are 3 escalations. One escalations, you can tell that, hey, you want to only run on a CPU, which will obviously give our level of performance. you want to accelerate further, you can go to GPU, right? Okay, right, and probably CDAC will be also coming with a quantum backend, right? And in that case, I think you can also put it to QPU. Okay, the particular. Let us try this. Is a very simple problem. We don't need a GPU for that. You can just use CPU and you can submit the job, right? And you can. What's happened? The measure gate is not there. Sorry. This is an error. So to do this, you have to actually apply a measure gate. Okay, which will actually measure this. Okay, so these C's are the classical registers, and the Q's are the qubit registers. Okay, so you can just run this, right, and you can just see what happens. Okay, so actually I have taken okay 3 qubits, but I can just switch off. I think I can just set this high level, and I can just tell one register and one memory and just see what happens, because then this will be very cool for us. Okay, so you see it gives an equal 0 0 1. Okay, but if you go to the state vector, right, you will see a certain change, right? You will see that this phase angle is 0, whereas this phase angle is 180 degree, which means that this is actually generated 0 minus 1 state, which is true because I have made Q0 as, and if you click it, you will see the same thing. Okay, this was your state. This was your state Q0 initially, so it was actually 1. But now if so there will be no change in the amplitude, no change in the probability, because 1 by root 2 both same, but there will be a change in the phase. Okay, the 0 will be positive and the 1 will be negative. But if I just set this to this, and I just set this to this as 0 instead of setting as 1, if I set this to 0, and if I run the same stuff, okay, you will see both becomes positive. So this result will be same. You will see the phase angle of also becomes same. So it becomes it's a 0 plus 1. So both are positive. So this is the way. These are the fundamental things you can do. Okay. Now if I go to the just to make it short, right? If I try to implement the QFT here, okay. I will just make a little bit more here. Let's try to manage maybe a 3 and 3. Okay, maybe on 3 and 3. Okay, and sorry. Okay. Sorry. So let me come back to the screen. We lost.
Sir, another browser, I think.
Oh, another browser is no, this one. This is the browser. Okay.
Correct.
Yeah. So these are also the other things. What you can check here is that you can check there are also another visualization where you can check the input and output states. Okay, so you can actually see the amplitudes, the phases, right? Because here all you can check in this particular visualizations, and you can also change the basis. So this is the 0 1 basis, which is in the across the z-axis. Plus minus is the x-axis, and plus I minus I is the y-axis. So a lot of things you can actually do in this particular environment, right? And this is very good. And you can also get the QASM code, which you can put it to other simulators, right? Okay, right, and you can take the code from other simulators, and you can just actually use that in the that will take it here, or you can take the code from here, copy it, and you can run it in other simulators and try to do that. Okay, so this is one thing, and then I want to go to the, okay, suppose I want to just go to the simple example what we did. Okay, suppose we want to so let's remove this. Okay, remove this edit this gate. I can just let me start a new file, maybe new file. Okay, let me start a new file and then try to work on this. Okay, so nature of QFT, if we try to do a QFT, it will be a sort like this. I think it will be a CP get, okay, which will be here. If I correctly remember, a CP get which will be here, and there you have to just, sorry, you have to just make it the target bit as 2. Okay, yeah. So this is there, and then the next will be this, and next the CP will be, CP get will be here. Okay, and then you have the Hadamard here. Okay, so this is there, and then you can have the swap gets. This I'm doing as a QFT. There is a QFT library also in the tool, but I am trying to use that particular. I think this will be with, sorry, the first one will be with, I think, sorry, first one will be with Q2, okay, and this one will be, I think there is nothing more required here, I think, for this particular case. Yeah. So, and then there will be measurements get, okay, measurements get for the classical measurement. So you measure the Q0, measure the Q0, and you have to look into that where you are actually measuring. You have to go for each of the quantum registers. You have to have an equivalent. You have to have a classical register, right? And then you can actually do a run, and in the CPU, so the job is still going on. Once the status is done, it will show completed. Okay, like the other tools, it will get a tick mark. It's still going on. Okay, and I think it's still going on. So, okay, so you can construct the circuit. Okay, right. One thing is that you can, that means you need to set this Q0, Q1, Q2 for your QFT at the present status, at the present level of the tool on your own by doing the normalization. Okay, you have to now normalize it, and you have to place it here and set the values of Q0, Q1, Q2. But I think very soon the normalization, the pre-processing will also be coming up. Okay, right, when you can actually just give your classical values and you just tell the normalize and set the quantum encoding, and it will set the Q0s, and then it will go working up. Okay, so due to limitation of time, you can just, all of you can try that. I'm not getting into that. There is also a there is also a library, I think, where you can get this. You can get this quantum algorithms library, right? If you don't want to do it handcrafted, right, you can go to this library where you can load a circuit. You can choose of your choice, 4 qubits, 2 qubits, load a circuit. It will do it for you. Okay, so good, right? So it is so good. This is a 4 qubit. and you can do it. Okay, so this is the way. Okay, this tool works fantastic, and I think there are a lot of libraries you will find here. Apart, although we're discussing today QFT, you have a lot of libraries. You have already, I think, rovers was discussed in the last class. So a lot of things are there, and you can and the students and researchers should actually work on this and work on. Okay, so I think I have 5 minutes to speak. If the time is there for me.
Yes,
5
sir.
minutes. Okay. Okay. So
Yeah,
so
you can take some more time, sir. If
okay.
you can explain
Okay.
on phase also, it's fine.
Yeah. So what I will tell tell all the quantum aspirants, all the quantum simulators, right? Who are trying to work on the CDAC tool, right? This is fantastic, and I hope that the libraries will be growing and growing. And I think you all have that. If you have good algorithms, if you have good circuits, right, you can also connect with CDAC to connect with this particular platform, and so people the other people in our country can use that. Okay, right, and this license is so good for training, for doing research and all these things. Okay, let me just close this tool, because obviously I think there will be better thing. I think sometimes CDAC will organize a full hands-on session, maybe physically. I think, but that will be more elaborative. But I think within the scope of time, I have just tried to give you some of the very interesting thing what Qniverse platform has. Okay, right, and you can explore it in the very good way. Okay, it's very interesting, and really it is a very good job done by the CDAC team. Okay, now I am just going to my presentation, the last part of my presentation. Okay, so what I do a quantum phase estimation, which is an application of the QFT, right? And I will see that what QFT we have, though QFT have multiple applications, quantum phase estimation is one of the things. Why quantum phase estimation is so important? Because when you are we have done a transform on a quantum state, right? And you know that the quantum state transforms associates a phase. Okay, right? And how we know that phase? Because that phase, if you see that phase actually needs to be stores the answer of the operation, right? And if you can extract that phase from the phase, okay, with some sort of post processing, I can get back actually the answer. Okay, what a quantum machine has done. Okay, so to know the state of a particular sample of a particular state, so know a particular state in a probabilistic distribution, the distribution what quantum generates. If you want to understand that what a state has been generated, you have to know its phase, right? And the quantum phase estimation is a quantum process by which you don't disturb the state, but you can still measure the phase of the state. Because if you disturb the state, then the state gets collapsed. Okay, so this is the thing. This is a very simple thing. So what you do in quantum phase estimation is a quantum circuit. Okay, write an unitary operator U, okay, which is within the complex domain, within the n qubit operator space. So that's why it's something like that. Okay, right, and satisfies the operation that U operated on a quantum state, generates a distinct phase e2 pi I theta. And can we use a quantum, after we do this, can we use a quantum process to actually estimate that phase theta? Okay, and that's the algorithm quantum phase estimate, because this will be used to understand what quantum states you have generated. Because unless you understand e to the power, what is e to the power 2 pi I theta associated with the state psi theta, you don't know what is the result of your quantum operation U. Okay, that's the importance of this. Okay, there are many applications. If you look into the factoring problem, right, which is actually the order finding, which is a fundamental algorithm for the Shor's algorithm, which is now going very strong in terms of the cryptanalysis. Okay, right, quantum random walks, right, which actually goes to the spectral decomposition of the graph, and that is also very important. Okay, right? And there are a lot of things. So now let us try to see that what was QFT. QFT, if you decompose QFT over the superposed states, right? Okay, so this will be the superposition, or a superposition on the QFT, and this superposition on the QFT will be can represent, this all can be represented with some notations. Okay, this can be represented as phi n. This is phi n minus 1. So there are a suffix. Okay, there are two suffix indices. Okay, this is actually 0 comma n. This is n minus 1 comma n, because this is actually, this is basically the n minus 1th term, and this is the first term. Okay, which is like this. So this is the way you define, and so we define as something called kn. Okay, which is a sort of a sequence of e to the power 2 pi 0 dot jk to jn. Okay, now this can be represented, because this e to the power 2 pi 2 pi 0 dot j, okay, this product across this exponential term. Okay, it means that you are actually done this particular part, okay, has been generated, okay, by this particular operation over a sequence of k, and this k is playing this particular role. Okay, right? And then what we try to do, this is the way we try to do. So suppose there are two, we take so how we set up the circuit, how we set up the function. So the function is set up in this way. So we have an unknown state psi theta, which we don't know. Okay, right? And we have an ancillary qubits, which is in superposition, right? And we try to, which is actually not superposition, it's actually n qubits. N qubits initialized with 0, which is 0n, right? And then we apply a Hadamard, and then 0n is now spreaded over 2 to the power n states. Okay, and that is represented by k, because k is 0 to 2 to the power n minus 1. Okay, because I apply a Hadamard on an n qubit register which is of length n, right? And then I try to apply a sort of transform, which is a control UK operation. And this control UK operation will actually generate a particular term called e to the power 2 pi I k theta, okay, on k. And what we try to do, we try to find out that what is this theta. And if we try to operate only on the ancillary register now, because this was prepared on the k superposition state. So from henceforth, I'm just doing on this particular part, henceforth I'm doing on this particular part, this particular part of my quantum register, which is the ancillary part. Okay, right? And then we do a QFT on this particular part, and this QFT will again generate, this is the QFT inverse, or IQFT, will actually generate the sequence on n, and this sequence on n will actually generate the phase term to the power n theta. And that is the way how we can actually measure this ancilla, and we can get this value without disturbing the actual state psi theta, which was unknown to me. And this is the way how we can actually measure the phase of an unknown quantum state. And this is very important to actually post-process the results which has been generated in quantum operations. Okay, right? I will not get in detail. So this is the way you do this particular operation. The control u to the power k cannot be done at one shot, right? You need to do it in an iterative way. So this is the way you first define the control u, and then you do it in an iterative way with actually the different qubits as control, and this together to actually generate this transform, which will be of this form. Okay, right? And then you do the QFT inverse, and you measure the ancillary register only to get the 2 to the power n theta part, right? And that is sufficient to give you the things, okay? So I'm not getting into details of this. You can go through the PPT. I will send the PPT to the CDAC team so that all of you can go through this and get back, because I'm already over the time, okay, right? And you can, a lot of applications are there, okay, for the quantum phase estimation, because when the fundamental quantum state gets evolved, right, you have to, it is due to the Hamiltonian, right? And the Hamiltonian transformation comes into the exponential part. Actually, your U operation in the continuous evolution of the system, U is actually exponential minus IHT. And to get that what U has, what was the Hamiltonian function of an evolving quantum system, right? You have to measure this phase part, this to know the Hamiltonian function, and that is very good in actually understanding lot of things in the lot of applications requires okay, this Hamiltonian, understanding the Hamiltonian or the eigenstate of the Hamiltonian function. Okay, so these are the things we can do. I'm stopping it here, right? And you can also, if I don't know whether I have used the Qniverse, right? You can also, I have this, so you can also have this quantum phase estimation. You can also have, so you can query me that, sir, will be in a quantum phase estimation, okay, right? You are giving the theta angle. Why? Because this is for simulation. So you try to see that if you try to find a theta angle, what should be your circuit and what should be your, so you can go with different that means you can have different factors of pi by 2. Suppose I go for pi by 8, right? And I go for a 3 qubit, right? And load it, right? It will be a circuit which I actually said, right? This is a control U operations on the phase part. And you first generate the superposition ancillary. This is your unknown Q2, which is known actually for you because this is simulation. And you try to find that if you give this particular as a phase, what will be your distribution, right? And you can run this simulator will help you to understand that, okay, what will be your measurement and what will be your distribution in the measurement, and you can just try to calibrate your circuit. You try to calibrate your circuit for a particular phase estimation. Okay, I stop here, and I think that the time I've crossed the time, and I should stop here now. Yeah. So
yeah, thank you, sir. It was a overwhelming, a deep session into QFT and QPE. Sir, can we have few questions from the
sure.
participants?
Please.
Okay. I'll just read out the questions for your easiness. One by Dibya Jyoti Sahu. They ask, does not encoding after normalization inherently forces us to work on a different samples than the one from which we start? Is that not a problem?
Oh, no. It's not. It's not a problem because normalization is a static component. Okay, that means you can always get back. But if you don't normalize, you cannot encode in a qubit system, because the qubit system, if you want to make a superposition of states, okay, the underlying rule is that you have to have a summation of all the amplitude squares. Okay, should be equals to 1, right? And that is what is required, because you have to understand. See, that means when you tell that, hey, I am just trying to compute in my classical computer, okay, so we cannot compute the classical computer unless we encode all our characters, all our numbers, all our floating points to some binary form, right? You have to do it, right? It's also an encoding form, right? And this is not difficult, because always you can get back from binary to the actual values what we can understand. Okay, similarly in the quantum domain, right, you have to encode it, otherwise you cannot set up the quantum system. Okay, a qubit state space. Okay, so that is the constant of the qubit state space, but that is not a difficult, that is the pre-processing part on the quantum system, and the post-processing part will take you back. Actually, I have a lot of good lectures where we show how the post-processing also can be done in some example use cases. So post-processing will take you back from the quantum states, okay, from the quantum normalized quantum states to the actual values in the classical states. Yeah.
Okay. Yeah. The next question is from Sumanta. Thank you, sir, for the talk. What should the areas to focus on if anyone tries to optimize the QFT? Or is it proven that this is the optimized circuit for QFT?
Oh, this is a very good question. See, the okay, the problem, the issue of optimization is that we can only say that this is the tilde best solution.
Okay.
You cannot, because that is where the people in optimization and circuit synthesis actually take a lot of interest. So we cannot tell. Obviously, we cannot tell that maybe a different technology will come up in the few years to come. A different type of that operations can come up, right? So at this point of time, right, this is the most standard circuit what we have, but there is that you can always try. You can always try if you can come up with a better optimized QFT. I'm not claiming that whatever has been shown here is the best optimized circuit. No, it's not that. But it is the most well used circuit. That's all.
Yeah. Apurva asked, currently for which application do we use QFT? Anyway, you have answered that in the later part of
Any Fourier transform work, right? Any Fourier transform work, you do it QFT. Still, there is a limitation in number of physical qubits what you can have, because what you showing, see, you still require time, right? Why you require time? Because this is running in classical CPU. This will be in nanoseconds in quantum. Okay, but quantum will not able to give a resource to us now at present. Okay, so once the quantum resource is pretty handy, okay, right, you will be fine to run QFT, right, and it will be so good for all of your financial algorithms, for your chemistry algorithms, for your signal processing algorithms, all good, so good.
Yes, yeah. The next question is by Vishal. I have a general question: how to develop new quantum algorithms? How to develop the intuitions?
That is a really big question. That means what I can say is that if you have to first start with exercising, okay, the algorithms which are already there, can we make a sort of an apply those algorithms? That's the first exercise. Apply the algorithms what are already there. Okay, try to formulate a quantum problem. That's the first step. Try to formulate a quantum problem, right? Formulate a quantum problem means try to find the way the superposition of states, okay, the coupling of entangled qubits, which give disruptive distributions, right, and interference, which actually works. Can we try to find these useful in any solving the problem? Then you try to find what are the fundamental ways to do that in your quantum circuits, and probably you can find one. Okay, so as you know, our group in India developed the quantum ant, right? And that's the algorithm what I can say, and a little bit of binary welded tree also one of our group with a Princeton group developed. So these are the 1.5 algorithm we developed in our entire journey of 20 years.
Oh, okay.
So you know that this is maybe that point of time quantum knowledge was not so available, tools were not so available, so we cannot try out. Maybe the next generation of quantum computing researchers, okay, will have some more tools and more support to develop algorithms, to test algorithms, and I think that is where the Qniverse plays a major role, right? How to motivate to simulate quantum algorithms, to test quantum algorithms, and then go ahead. Yeah.
Right. Thank you. So the next question is by Vishal Pandey. Should not the control of the CP gate be on the source qubit beside the Hadamard gate, which you showed in your circuit?
No, because if you see the operation is on 0 plus 1 the Hadamard gate generates, and you have to force the 1, and you have to force the phase factor on the 1. Okay, now if you see the control CP gate matrix, right, it has the transform on the last on the last, what I can say, on the last corner. So the last corner walks on the 1 1. Okay, so the last corner walks on the 1 1 cell, so which is a single 1, and then 2 1 and 3 1. So okay, so that means, and that particular operation is acted upon by a qubit on a particular state which is in the plus 1. Okay, so plus 1 comes from the Hadamard, from the superposed state, and the previous qubit, the other qubit enforces that this actually works upon on that particular state. So that's the way it works. Yeah.
Sir, Raghavendra asked, in QPE, is it mandatory to know both unitary operator and eigenvector?
You have to know the unitary operator, not the eigenvector.
Okay.
Okay. Yeah.
Yeah. Sir, there is a few more questions. Is it okay to take some
sure.
three?
Please, yeah.
One Mr. Parmanand, he asked, why is normalization critical for quantum states, and how does it differ from classical probability distribution?
Oh, this I said now, because if you see the quantum state space, right, you have the probability of measurement on a particular state is maximally 1. Right? Now in a real quantum, this probability is distributed. So now, as the maximum value of measuring a particular state is 1, then you have to, if you distribute that 1 among all the superposed states, okay, then you have to normalize it such that, okay, the probability means the square of amplitude summed for all the states should be 1, because at the that obviously I will not tell the best case scenario of the quantum, it's actually the worst case scenario, but in the best case scenario compared to classical is 1 state is only measured, 1 state is only high, and that can be only maximally 1. So now this 1 gets distributed among all the superposed states now. So ultimately the probability of all the states summed to will be 1, and that's why the amplitude of all the states squared will be summed to 1.
Okay. So the next question is by Dilip. How to use quantum machine learning for image processing?
Oh, this I will check in offline, and please connect me. So, okay, so these are intensity values. So in the machine, in the image for intensity values. So, okay, so the amplitudes are equivalent to intensity values, right? And you have to encode the positional XY pixels in terms of superposed states. Okay, so suppose you have an n cross n image. Okay, so you have to represent it at log n cross n number of qubits. If you want to make the entire block ones, then is the position. Then you encode the pixels, and the values of the pixels will be normalized in the superposition. Okay, so that you can represent that qubit state space. Yeah.
Okay. Sir, at the interest of time, dear participants, if you have any more questions,
please
you can directly connect with.
Yeah. Push it to the organizers.
You can directly connect to with the professor,
or me also. You can connect to the organizers also, right? I will be very happy to answer the questions. Yeah.
Yeah. Thank you very much, sir. It was a very deep discussion and very insightful. You have taken your 1.5 hours, explaining QFT and QPE for us. Thank you very much. We will connect you in future in another way. And thank you all the participants. Hope you had a wonderful session this week. And next week we will meet you. Thank you all.
Thank you all. Sir. Thanks to Siddharth, and thanks to Santosh, and thank you all the participants. Okay, please try to build a workforce for quantum for our country. Okay.
Right.
Okay. Thank you all. Thank you.
Thank you,
thank
sir.
you all.